Hello, welcome to this lecture. Today we are going to derive an expression for height capillary rise in case of capillary tube dipped inside certain liquid. And this action is called as capillary action. Now here is a capillary tube of certain diameter or radius r, and it is dipped inside a certain liquid of density rho. Rho is a density of liquid. It can be water, it can be mercury. So depending on the surface tension of this, depending on the density, you can have a rise or fall of liquid inside the capillary tube. If it is a case of water, you will have a rise in the liquid relative to the surface. If it is a case of mercury, you will have a fall in liquid level relative to the surface of liquid. Now we will just take an easy case, that is a water glass. Capillary tube is made of glass and here it is a water. Obviously there is a rise in liquid level relative to the surface of liquid, and this is a height. So we have to find out how much height you can expect for the meniscus from the surface of the liquid. And does it depend on the radius or diameter of this capillary tube? Does it depend on what liquid you take? So we are going to get one expression and we will just find out how it depends on other parameters. So we have got, I've just drawn a magnified diagram here, and this is actually liquid, and from this is a surface, and relative to the surface you got this much rise in liquid. And because of the surface tension, you have got this liquid rise. That means the force of adhesion, that means the force between glass and the water molecules, is more than force of cohesion, that is force between these water molecules. So because of that you can have this rise in water. Anyway, there is a surface tension which always acts along the surface. So this is a surface tension. So this is actually meniscus. When you see from the top of this capillary tube, so this is a top view actually. Here you have got a surface tension. This is a theta, angle of contact, which is angle between a tangent drawn to the surface with a solid surface, and obviously this is a surface tension along the tangent, and this is theta. Now I am resolving this t into two components. One is the horizontal component, that is t cos theta, another one is the vertical component, t sin theta. It does not happen only at one point, it happens throughout the circumference. But when you take a capillary tube and when you dip inside, you will have a meniscus, and the top view of meniscus will be like this. So that the surface tension, this is a force which acts always tangential to the surface all over the circumference. So that's why you have to resolve this t into two components everywhere throughout the surface. Now I will find out how much is the weight of this liquid inside the capillary tube relative to the surface. So that weight of liquid inside capillary tube relative to the surface is equal to mass of the fluid inside this into gravitational acceleration. I will just write this mass of the fluid or liquid in terms of density. We know that density is equal to mass by volume, and this implies mass is equal to density into volume. So this mass, this weight is equal to, mass is actually density into volume of this is actually area into height, because this is a height, this is the area of the cross section of the capillary tube. So that is rho into volume. Volume is nothing but area into height into g. So this is weight rho. What is area of this cross section? It's a circular cross section of a capillary tube. Obviously it is pi r square h into g. So this is a weight corresponding to this liquid from the surface. Now what makes the liquid rise from the surface? Because of surface tension you got, what component makes the liquid to rise from the surface? Is it a horizontal component or vertical component? Obviously this vertical component, that is t sin theta, cancel all over, because if you take a circumference, everywhere it is opposite and you will have a cancellation of all the forces. So this T sine theta will disappear. Only the vertical component which acts along the vertical direction upward, T cos theta, which acts all over the circumference, is responsible for the rise in the liquid. So that's why T cos theta is actually the horizontal component of surface tension, which is responsible for our rise in liquid. Now, how much is a force? T is actually the surface tension. So, how much is a force? So, we define surface tension as force acting per unit length. So, this force for a given imaginary line of certain length L. Now, this force, that is force due to surface tension, is surface tension into length. Now, in this case, for this meniscus, since it is a circular, this T cos theta everywhere acts upward for entire circumference. So, force is equal to, this T is actually T cos theta, because T sin theta just vanished, and this length is actually circumference, because T cos theta acts all over the circumference. So, that is the circumference of the circular cross section. When you see from the top, actually it is 2 pi r. So, this is actually the force corresponding to the surface tension T. Let me take this equation number 2. Initially, the water will rise when you just dip. As soon as you dip inside the water, water will rise to the capillary tube. But after a certain time, water will stay steady at this height. Why it happens? Because this weight and the surface tension force balances. That is called equilibrium position, equilibrium case. In equilibrium condition, the weight is balanced, the weight is which is downward direction, and balanced with the upward force due to surface tension T cos theta. So that is equation number 1 and 2 have to equate. So rho pi r square h into g is equal to f T cos theta into 2 pi r. I want to know what is the expression for height. So I want this h is equal to, so this T cos theta 2 T cos theta, 1 r I lose, and pi also I lose. So I left with this rho g r. So this is an expression for height of liquid inside the capillary tube relative to the surface. So we got to know that this height h depends on the surface tension. If the surface tension of liquid is more, obviously the height or rise in the liquid relative to the surface is obviously more, and it is inversely proportional to radius. If you take a capillary tube of greater radius, the height from the surface is obviously less, and it depends on the density as well as theta. So in case of glass, water, we have theta which is around 13 degree. If it is a very pure distilled water, we will get it is 0, we will get as 0. So cos theta is approximated 1 because theta is very, very less, 30, 0, cos theta approximated 1. So you'll get h is equal to 2t by rho g r. So this is for liquid case. Which liquid? That is water. So water case, you got the height which depends on the surface tension, and it is given by 2t by rho g r. So thank you for watching this.